Thank you, Steve, for the introduction. And as Steve alluded to, this is actually my 32nd year of involvement with the Hubbard Brook Ecosystem Study. And I have to say, it's very gratifying to look out in the audience and see so many familiar faces of people that I've worked with or known over, scary to think, the last 3 decades. Great to see so many new faces of friends and supporters of the Hubbard Brook Ecosystem Study. And I think we would all agree, so great to see the new and eager faces of the next gen of the Hubbard Brook Ecosystem Study participants. So, seems to be a little bit of a theme here. David Sleeper asked me about 2 months ago whether I would give a talk on, let's see, that's not quite. Well, we'll go with that. So anyway, he asked if I would give a talk on climate change in Hubbard Brook, and I too was a little bit intimidated by that task, until I realized that even though I came of professional age, right, in the heyday of acid rain research, that is in the 1980s, I really have spent the majority of my professional career either trying to understand climate change, trying to study climate change, or trying to communicate climate change. And so what I decided to share with you today was my own personal perspective on the evolution of our understanding of climate change and its impacts at both the global scale and the local, the Hubbard Brook scale. And I want to do this by first and foremost talking about what we know and what we know well, and then kind of building to what I see as an emerging area of a critical need to know. And of course, a critical need to know, which is off the side of this screen right now, is how the new normal of extreme events, and we've heard a little bit about that today, but of how extreme events may be shaping future forests. And so I decided to do something a little bit differently today, and don't worry about seeing the fine print in the back. So I decided to do a data visualization project, okay? And this is a little bit different way to talk about our information. And any of you who've been looking at these on the internet at all, it's basically meant to be a standalone project. And if I had infinite time and resources, this would be a touch screen, right? And you could go up and you could touch what you wanted to look at in more depth. But since I have neither infinite time nor infinite resources, you're going to have to put up with listening to me walk you through this visualization. So the visualization was constructed as 4 different parts. I know it's hard to see in the back, but we'll zoom in on this in a little bit. But the lower part is meant to tell the story of increases in atmospheric CO2 and concomitant changes in temperature over the last 800,000 years. The middle and the left part is meant to show a timeline of the increase in our understanding, so landmarks in the increase in our understanding of climate change and its impacts, both at the international global scale and at the Hubbard Brook scale. The red arrows are meant to represent our growing need to know. So need to know about extreme effects and their impacts on this template of a changing climate. And finally, what I hope is rising to the top will be some discussion of future directions for frontiers in extreme research. So, let's step back 800,000 years. And this is atmospheric CO2 concentrations over the last 800,000 years. And if we go to pre-modern times, this is reconstructions of atmospheric CO2, largely from CO2 in gas bubbles trapped in ice cores from Antarctica. And basically what it tells us is atmospheric CO2 is bounced around a lot. We know that over the last 800,000 years, but it's bounced around between about 160 and 300 parts per million, with a mean of 285 parts per million. Those are important numbers. We also know that at the beginning of the Industrial Revolution, as we began to convert fossil fuels and tropical rainforests to atmospheric CO2, CO2 concentrations began to rise. And we know that they ended up at about 315 parts per million in 1958. And we know that because Charles Keeling started measuring CO2 in 1958. And what started as perhaps a modest project and maybe even an obscure record has since become perhaps the most powerful and the most important long-term data set in the history of humankind. So we know that atmospheric CO2 was 315 in 1958, 59, and we know that it's increased steadily to about 400 parts per million as of about a week ago. To the best of our ability, using IPCC emission scenarios and the latest generation of Earth system models, we might anticipate that CO2 would go up again to about 560 to 900 or 1,000 parts per million by the end of this century. And the point of this visualization is to give you that visceral comparison of where CO2 was, where it is now, and where we might be going. So as goes CO2, so goes temperature, of course. And I'm not going to make you dizzy and zoom in on the past 800,000 years. But if we were to do that, you would see that the reconstructions of mean global temperature follow the reconstructions of atmospheric CO2 very closely. I personally like to work with the thermistor record. These bars show mean annual temperatures, global temperatures, as a temperature anomaly, which is the difference in this case from the 1990 to 1999 mean. And as we all know from this record, mean global temperature has increased by 1 degree C over the last 100 years. And we also know that the 10 warmest years on record have been in the last 15 years. So if you think it's been getting warmer, it really has been getting warmer. Again, if we look to the future and we use those same emission scenarios and Earth system models, we might anticipate that mean global temperature would increase by another 0.6 to upwards of 4 or 5 degrees C. And again, we try and put this, a point of the visualization is to give you that visceral feeling of where we've been and where we might be going. So as you put more energy into the atmosphere, the oceans, and the land, by the laws of physics, we have to change the hydrologic cycle. And we now have good evidence that there has been an intensification of the hydrologic cycle over the last 100 years, and we anticipate that this will continue during the next century. So we would expect changes in the magnitude and distribution of precipitation. And germane to this talk is increased frequency and severity of extreme events. And I give some examples in red there. So I'm going to move on to the next part of the visualization, and that's this increase in knowledge over time. This is the global scale, the international record, and I always anchor this in 1958 with the start of the Keeling curve. And by the early 1990s, there was enough consensus that something was going on that the international community came together and began to make these series of IPCC climate assessment reports. First one in 1990, then 1995, then 2001, then the last one was 2007, and as I believe Fred pointed out, the next one is anticipated to come out next year. Now, if you're like me and you like to read the reports for policymakers, the language in these reports is fascinating. So if you read the language in the first 3 reports, they're really quite mild. And these reports surmise that there might be a change in mean global temperature. And they surmise that this might be due to some sort of human influence. If you fast forward to 2007 and what we anticipate the language to be in 2014, we begin to see words like warming is unequivocal and 90% certain that humans are the cause. And our glimpse of the 5th assessment report, there is incontrovertible evidence that atmospheric CO2 has increased, and scientists are virtually certain that this is caused by human activity. So, it's kind of like watching your kids, grow up, right? When they're really young, the early part of this seems to go on forever, and then all of a sudden you look back and, they're all grown up and you just feel like, well, what happened? So this is really an amazing record over a fairly small time period. I now want to look at the Hubbard Brook timeline, and this is meant to show benchmarks in our understanding of climate change at Hubbard Brook. And if your favorite benchmark is not there, I apologize in advance because there are many. So as with the CO2 being grounded in 1958 with a Keeling curve, I like to found our record in 1955, which is when the Hubbard Brook Experimental Forest was established. And we started taking measurements of hydrology and meteorology as early as 1956. So that was before Charles Keeling was starting to measure atmospheric CO2 concentrations. We're here to celebrate the establishment of the Hubbard Brook Ecosystem Study in 1963, where on June 1st, the first water samples were taken. And as we've heard, shortly after, it began vegetation surveys, bird surveys, mammal surveys, salamander surveys, and all critters, large and small. Landmark, of course, is 1968, when acid rain was discovered, and this precipitated, if you will, on quite a number of acid rain experiments. And I just didn't put anything here because I want to focus not on acid rain, but on climate change. So about the time the second and third, or really the second assessment report was coming out, which was beginning to talk about the fingerprint of climate change on the global scale, we were beginning to recognize the fingerprint of climate change on the local scale. And we started a series, or we, this is the royal we, a series of climate change studies and experiments. And just briefly, 1996, Peter Groffman and colleagues started the first freeze experiment. 1998 was the ice storm of 1998, and a tremendous amount of research went into studying that. The second and third freeze studies were in 2002 and actually 2009. 2010 was the first ever in the world, as far as we know, ice storm manipulation experiment. And then 2013, Pam Templer and her colleagues have started CCASE, or the Soil Warming and Freeze Study. So we really can lay claim to a very rich body of knowledge in our monitoring, in our experiments, and also our modeling. And I'm just giving a nod to modeling. I'm not a modeler, but a lot of that is going on as well. And so what have we learned? Again, I can't tell you everything, but I want to tell you some of the highlights. As we said, mean global temperature has increased by 1 degree C over the last century. We've actually seen a 1.3 to 1.6 degree C increase in temperature at Hubbard Brook, depending on which record we're looking at. We've also seen a change in the water balance. We've seen, as we heard, a slight increase in precipitation, and with that comes a slight increase in stream flow. It's kind of curious that our increase in stream flow is a little bit greater than our increase in precipitation, and when you do the simple math and you subtract that, you get a decline in evapotranspiration. And that's a little bit curious, since evaporation tend to go up with increasing temperature, and that's an area of very active research right now. In terms of snow, we're in northern New England. We all love our snowpack and our winter activities. Here are 3 metrics of snowpack, and all 3 of them have gone down by about 25% in the last 50 years. So this top graph, I know it's hard to see in the back, is maximum snow depth. This has gone down by 26 centimeters. Next one is maximum snow water equivalent. This has gone down by 8 centimeters. And then the last one is snow cover, which has gone down by 22 days. And of course, if you're in the ski business or the snowmobile business, or you just like to go out and cross-country ski or enjoy the winter, 22 days is a lot in 50 years. During this time, we've also studied a lot of winter climate events, and I would suggest that one of the signature observations of the Hubbard Brook Ecosystem Study climate change is this link between snowpack, soil frost, and nitrogen leaching. And this is a cartoon that shows on the left what might have been our more typical situation, where we might have had a meter of snow in the winter, which nicely insulated the ground and the roots of the trees. On the right, we have perhaps where we are now or where we're going. With little to no snowpack, we still have freezing temperatures, and we might get deep soil frost. Myron Mitchell, who is in the audience, I was very happy to see earlier today, did a paper as early as 1996. Myron, it probably doesn't feel all that long ago, but where basically looked at some of these peaks in stream water nitrate concentrations and noted that they were concurrent with years that had deep soil frost. And this begat, if you will, a generation of freeze experiments. And somehow, first Peter Groffman and colleagues, then Pam Templer and colleagues somehow convinced their grad students to go out in the middle of winter, right? I don't know how they did this, and shovel plots way up in the watersheds and remove the snow for the first 6 weeks of the winter. That caused a deep freeze of the soils. And then the following year, they saw the legacy effects of that, of decreased fine root production, increased nitrogen, phosphorus leaching, and increased N2O fluxes. So they basically nailed this relationship between snowpack, soil frost, and changes in the biogeochemistry of the system. So ice storm of 1998, many of us lived through it. I was in Maine. We were without power for 14 days in the middle of January. This was a huge storm that affected most of the northeastern United States and eastern Canada. It put millions of people without power for several weeks at a time and caused $16 to $17 billion in economic damage. Here at Hubbard Brook, we were hit fairly hard by the ice storm, but we were also tremendously well poised to study the ice storm. And we were able to mobilize our resources and actually get some additional resources from the Forest Service and the National Science Foundation to go out and do what is the most comprehensive study of an ice storm anywhere in the world. And we learned a lot about the ice storm, but just one tidbit I'll put up here is this graph on the bottom. The ice storm is here in January of 1998, and you can see stream nitrate going up the following year, this decoupling of above and below ground nitrogen processing. And this has begat, again, maybe a new generation of ice storm experiments. As I alluded to before, in 2010, we went out and we did what, as far as we know, is the first ever ice storm experiment, where we actually used firefighting hoses. We sprayed water up in the air. It came down in a fine mist on a very cold day. And we actually virtually recreated the 1998 ice storm, and looking at things like coarse litter debris and fine litter debris and openings in the canopy was very similar in extent to the 98 ice storm. And so now we want to use this methods, and we have a proposal into the National Science Foundation to do larger scale study on this. So tremendous amount of information from Hubbard Brook. And we got together, actually probably 2007, 2008, with 50 of our closest friends and colleagues in the Northeast and Eastern Canada, and we did a synthesis. This is my next prop. So we did a synthesis of climate change, trying to take the look back last 100 years to see how climate had affected forests already, and then look to the future. And again, we have copies in the back. Feel free to pick one up. But we looked at impacts on biogeochemistry, the water cycle, and the biology. But we had a fatal flaw, right? And I apologize to the authors in the room, but we didn't really consider extreme events. And I would like to suggest that extreme events may have equal or greater impact on the structure and function of terrestrial ecosystems than this slow, gradual increase in CO2 and some of the other global change drivers. Moreover, we cannot take what we know about past extreme events and just extrapolate that into the future, because we need to understand future extreme events on this template of an underlying change in climate. And I'm going to give you two examples of how that might work. So this first one is winter rain events. So anybody from the area knows that we often get January thaws, and we get rain in January, and sometimes we get a lot of rain in January, which is a big winter rain event. If we look back to 1963, we would have had nice, thick, meter-thick snowpacks. Rain would come down on this. Those snowpacks contain nutrients and acids, would melt away, and we'd have this big chemical event with acid pulses. And a lot of effort went into understanding these acid pulses based on these winter thaws and winter rain events. Well, fast forward to this year. This is a picture that Scott Bailey took at the end of January in 2013. We had a very patchy snowpack. We had a lot of ice. We had a lot of frost in the soils. Got virtually the same event, ran right over the surface, right into the stream channel, right over the weir, taking all kinds of ice and chunks of rock and debris and all kinds of things with it. So this was really a physical event this last year. Now, if we look to 2063, the next 50 years, we would expect little to no snowpack and much warmer soils. And in this case, the same event might just infiltrate through the soils and trickle down into the stream. So in a sense, you could say this is a softer, gentler world in terms of winter rain events. However, we have other events. In this case, I'm going to use the example of late spring frost where it might not be as gentle on the ecosystem. Here I'm going to use the example of sugar maple as a common species around here. And I'm going to talk about a frost, and I choose May 10th because there was a May 10th frost in 2010. So that's an example. So overall, we would expect our last killing frost to be occurring earlier and earlier in the season, but we also expect wacky weather. So we do expect or anticipate that we would continue to have these kind of crazy late frosts. Well, for sugar maple, if we look at the phenology of sugar maple, and I'd like to thank Nina Laney for providing me with some of these pictures and data, but if we look back at 1963, that May 10th frost wouldn't really have too much of an impact because the buds wouldn't have broken yet. Here, the phenology has advanced considerably, and now about 50% of the sugar maple leaves are unfurled by May 10th. And if we have a frost, then there could be significant damage to these young, sensitive leaves. Fast forward 50 years, we expect the entire canopy to be out by May 10th. And so if we have a late frost or a late snowstorm, there might be almost catastrophic damage to the canopy. So the point, again, is that we need to understand extreme events on this template of an underlying change in climate. So the fourth part of my data visualization is to talk about, well, what do we need to do? And I've had the good fortune to have participated, actually organized, 3 conferences on extreme events this last year. And so I'm kind of reporting back from the global change community. And the community has talked about 4 different areas. First is theoretical considerations. And this is that same concept that I've mentioned a couple times, understanding extreme events on the changing template of climbing, or on the template of changing climate. Another important area that's been emphasized is the need to understand extreme response thresholds and tipping points. And this is a figure put together by Melinda Smith, which emphasizes that we need to figure out what these tipping points are, below which there are either no ecosystem effects or just transient effects with fairly rapid recovery, and above which we have either prolonged recovery in the decadal cycle or an actual state change. So some of the new generation of experiments should be designed in search of these elusive thresholds and tipping points. And so we don't need to just do an experiment with one level of perturbation, but multiple levels, and one of those levels needs to kill the system. We've been very careful about not killing trees when we need to kill trees and find out at what point this is. And we've done a lot of this hard work at Hubbard Brook. We figured out how to do ice storm experiments, and we have a big proposal in to do that, multiple levels, multiple years. And Pam Templer has C-Case, which is looking at multiple levels of freeze in addition to soil warming. So we're really kind of in the forefront, of beginning to think about and do some of these new generation of experiments. We also need to rethink our long-term monitoring to some extent. We need to have a system in place where we can understand the anatomy of these storms as they go through. And I am really proud to say that at Hubbard Brook, we are in the process, the final death throes, if you will, of replacing what was the state-of-the-art system in 1955, which was a mechanical system with strip charts and pens and all of that, with a new state-of-the-art system for the 21st century that Michael alluded to this morning, where we're using digital sensors, wireless sensor networks, and we're getting high-frequency data in near real time. So we can understand the anatomy of these storms as they go through. But just having the sensors out there doesn't really help us. We need a new approach to how we do our monitoring, and so we're beginning to assemble RAT teams. So these are rapid assessment teams where we really try to be ready for these events, have everything out, deployed, functioning, and then go back to the safety of our own homes, watch the event pass over us, and then very quickly get out and retrieve the data and be able to report back on what's happened. So rapid assessment teams. The final approach is models. I am not a modeler, but I do want to acknowledging that the modeling is very important. And the only comment I really want to make is my modeling friends and colleagues are working hard to try to incorporate the concept of extreme events into our ecosystem and Earth system models. So the final point I want to make is we can't just take one of these approaches. We really need to work on all four of these fronts, and we need to integrate and synthesize what we know. And I'm going to end with the comment that I think one of the real strengths of Hubbard Brook is this ability to integrate what we know from all kinds of different studies, different people, different times in a record, bring it together and synthesize what we know on an ecosystem level. So I look forward to the next couple of decades, maybe the next decade, of being able to really confront climate change in the 21st century and really begin to evaluate how extreme events are going to shape our forests. So that's what I got.